In this video, we discuss differentiating and anti-differentiating power series. And I'm using this notation now. I've got a power series. These coefficients these a sub n, they're just coefficients, they're numbers. Those numbers tend to change for the values of n for the different terms for different terms of the power series. I've got x minus a constant, that constant's the center of the series, raised to the n, and that represents a new function, f of x. Now this will converge sometimes. It may converge at x equals c only. It may converge in an interval around c, and that interval may or may not include the endpoints, or it might converge on the entire real line. In this section, we're talking about how to find the derivative of a function f that looks like this, how to find its antiderivative, and then there is a relationship between the intervals of convergence of f prime, and its antiderivative. All of the derivatives that are well-defined and all the antiderivatives that are well-defined will have this relationship as well. So let's just look at a series and explore this idea. Let's say somebody asks you to find the derivative of the following function. So I have f of x equals the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 all divided by 2n plus 1 factorial. If I'm asked to find the derivative of this, it often helps me to just expand it. Remember what it is we're looking at. When n equals 0, I've got negative 1 to the 0, so that's 1, times x to the 2 times 0 plus 1, so that's x, all divided by 1 factorial, which is, of course, 1. And then when n equals 1, we get the following. Negative 1 to the first is negative 1. Then we've got x to the 2 times 1 plus 1. 2 plus 1 is 3. And then we're dividing by 2 times 1 plus 1, so that's 3 factorial. I don't know, do you guys see the pattern? When n equals 2, what do we get? Negative 1 squared is a positive 1. If n is 2, we get x to the 2 times 2 plus 1, that's x to the 5th. And the 2n plus 1 is here, and it's the same thing factorial in the denominator, so if that's a 5, this should be a 5 factorial. And I hope you see the pattern. That negative 1 to the n causes the sign to alternate. Negative 1 to the 0 is 1, so it's positive, then negative, then positive. The next one will be negative, then positive, and so on, and it'll continue forever like this. And notice also that no matter what n is, 2n plus 1 is an odd number. If n is an integer and I double it, it's going to be an even number. And then if I take an even number and I add 1 to it, it's going to be an odd number. So we see when n equals 0, we got 1. When n equals 1, we got 3. When n equals 2, we get 5. So it's 1, 3, 5. The next one's going to be 7. Then one after that's going to be 9, and so on. So we'll have x to the 7th there. In the denominator, we got that same number, that exponent factorial in the denominator, so we've got 7 factorial there, and x to the 9th over 9 factorial there. So this is our expanded form of this power series. Now, if I want to take the derivative of this, it's actually not that bad at all. If you know how to take the derivative of a polynomial, you can take the derivative of a power series. The derivative of this can be found in the same way that you would take the derivative of a polynomial. You just take the derivative of each term separately. So I've got x minus, I'm going to factor out those constants, 1 over 3 factorial times x cubed, plus 1 over 5 factorial times x to the 5th, minus 1 over 7 factorial times x to the 7th, minus 1 over 9 factorial times x to the 9th, and you keep going. So you're differentiating, you're just differentiating term by term. The derivative of x is 1. Then I bring my constant down, And the derivative of x cubed is 3x squared. Bring the constant down. Derivative of x to the 5th is 5x to the 4th. So remember, we bring the power down, multiply by x to the 1 less power. And we're doing this for all of these guys. So we have 7 times x to the 6th. Bring the constant down. 9 times x to the 9 minus 1 is 8. Oops, and I think I missed my sign somewhere. Plus, positive, negative, negative. That should be a positive. There we go. And you keep going. Okay, now this actually simplifies a little bit. Got 1 minus, and that 3 cancels with the 3 over here. This is 3 over 3 factorial. That's 3 times 2 times 1. So the 3's reduce, and you end up with a 1/2 out front. Or over here, you've got a 5 over 5 factorial. You see the 5's reduce? And so you've got a 4 factorial left. And the same is true with the 7 and the 7 factorial. The 7's reduce. And you've got a 6 factorial left. It's kind of an interesting pattern, isn't it? So it looks like I've got a 1 minus, and I'm going to think of that too as a 2 factorial. X squared over 2 factorial. Then I've got, it should be a plus. I keep messing up my signs. Plus x to the 4th over 4 factorial. Minus x to the 6th over 6 factorial. Plus x to the 8th over 8 factorial. And we keep going. So it's kind of cool. Like, look at that one. It's got all the odd powers of x. We've got a 1 factorial, 3 factorial, 5 factorial, 7 factorial. The exponent and the number we're taking the factorial of in the denominator match, and the signs are flipping, positive, negative, positive, negative. The same thing is happening here, positive, negative, positive, negative. But this one, its derivative has all the even terms. The original function had all the odd terms. The derivative has all the even terms. Okay, so that's one way of taking the derivative. You're just taking the derivative term by term, but most of the time we don't want to write our power series this way. We'd like to write it in this compact form. The problem with this form is we don't know if the pattern continues on forever after this. We would assume it does, but we don't know. It's not clear that it does. This tells me every term looks like this, and we're adding from n equals 0 to infinity, just forever, and they all look like this. When n equals 100, I know that this is going to be negative 1 to the 100th times x to the 201 divided by 201 factorial. I know exactly what it's going to be. Not so clear here. So even though this is what we're doing, we're just taking the derivative term by term, we'd like to write it in this more compact form. So we're going to do it slightly differently. But if we remember what sigma notation means, what sigma notation represents, then we'll see this is exactly the same as what we just did. If f of x is this infinite series, so it's the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And we're taking the derivative. Remember from calculus 1, the derivative of the sum is the sum of the derivatives. So we can actually bring that derivative operator inside our summation. And we've got this now. And remember, you're differentiating with respect to x. I know it looks like you've got all these n's everywhere, and that's another variable. It's not. For a particular term, that n just tells you what the exponent is, and it tells you what that denominator is. But the variable itself is x. So the negative 1 to the n and the 2n plus 1 factorial, you can bring those out. And all you're really doing is taking the derivative of the x to that power. just like we did over here, I factored out my constant, that's my constant, and then I took the derivative of x to the 5th, and I got 5x to the 4th. I factored out my constant, and I took the derivative of x cubed. We're doing the same thing here, it just looks different, but it's the same thing. We're just doing all of them at once. Instead of doing that power rule 5 times, I'm going to do the power rule once, and it's going to represent infinitely many power rules all the way to the end. So we said the derivative of the sum is the sum of the derivatives, factor out the constant, and then just take the derivative of this part. So we've got the sum as n goes from 0 to infinity of -1 to the n over 2n plus 1 factorial. And the derivative of x to the 2n plus 1 is 2n plus 1 times x to the 1 less power, so x to the 2n. Now that's the answer, but we might want to simplify it. Notice I've got a 2n plus 1 right here and a 2n plus 1 factorial. Kind of like we had here. We had a 3 and a 3 factorial, a 5 and a 5 factorial, a 7 and a 7 factorial, a 9 and a 9 factorial. In general, that's 2n plus 1 and 2n plus 1 factorial. Well, we can break that up a little bit, because we know 2n plus 1 factorial has a factor of 2n plus 1 in it. So we can say that that's the same as 2n plus 1 times 1 less than that, which is 2n. And 1 less than that, and 1 less than that, and you're multiplying them all together, so that's going to be 2n factorial times x to the 2n. And that means these guys reduce, and you end up with this. The sum as n goes from 0 to infinity of -1 to the n times x to the 2n over 2n factorial. Now that actually looked a lot more long and involved than it is. So I'm going to write on the next page just a basic derivative rule. All you do is bring that derivative operator inside and focus on the x part. Focus on this. So factor out the constants and then take the derivative of this guy, the part that involves x, and hopefully you've done the algebra at the beginning so that when you take the derivative of this, you're just using the power rule. You shouldn't have to use the product rule, the quotient rule, the chain rule. None of that should be necessary if you've simplified. We try to always have a simplified form that involves just x to some power so that it's easy to take this derivative. And then we did some algebra at the end to make it look pretty, to make it look more like this, where you've got the 2n as the exponent, so those are the even powers of x, divided by that same power, or that same number, factorial. And the -1 to the n gives you the alternating sign. Okay, so let me give you the rule. So if f of x is equal to this, then its derivative can be found this way. You're taking the derivative with respect to x of f of x and even though it looks like alphabet soup and you've got all these variables running around, it's really not. That's a constant, and that's a constant. We're taking the derivative of a function of x, and this is just x minus a constant to some power. So we use the power rule, which makes sense for power series because we've got powers of x. You bring out the constant, and you bring the derivative of the sum is the sum of the derivatives. You bring the derivative operator inside. And then you just take, whoops, lost the cap to my marker. You just take the derivative of that guy using the power rule. So you have a sub n times the derivative of x minus c to some power. It does require the chain rule. It's a very simple chain rule. You get n, so you bring the power down, and then you multiply by x minus c to the 1 less power, and then you multiply by the derivative of the inside by the chain rule. Derivative of x minus c is just 1. Now, if you look in your book, it's not going to look this way. They're not going to start with n equals 0. And I'll tell you why. in general, when n equals 0, well, what do I get? A sub 0 times x minus c to the negative 1. Well, if n is 0, this is just 0. And that actually makes sense because if n is 0 here, we just got a sub 0, and the derivative of a constant is 0. So we don't want to add that 0 at the beginning of our series. So most of the time what they do, instead of writing this, they write this. We're going to change that value of the index to be 1 so that we start with the first non-zero term. But remember, the reason why that index increases by 1 is because when n is 0, we get 0. Okay, so that's the derivative. And I bet you can figure out how we find the antiderivative. We also antidifferentiate term by term. The antiderivative of the sum is the sum of the antiderivatives. Just like if you were taking the antiderivative of a polynomial, you'd look at one term, take its antiderivative. Look at the next term, take its antiderivative. The same is true here. Everywhere you have a constant, pull it out. This is constant with respect to x, so we pull it out. And now we're just taking the antiderivative of x minus c to the nth with respect to x. And remember, for a particular term, n is a number, c is a number. So I'm just using the power rule again. So we have the sum as n goes from 0 to infinity of a sub n. And then to take the antiderivative of this, using a very simple u sub where u equals x minus c, we get u to the n plus 1 divided by n plus 1. And since du and dx are the same, I don't need to actually write out that u substitution. This is u to the n du if we do the u sub. Now, you also need a constant of integration, but we don't want to put the plus c over here because sometimes that can be ambiguous. It might look like we're adding infinitely many constants together, and we know that diverges. So it's actually this plus one constant of integration. So I like to put the constant of integration out front. A lot of textbook authors do, just to make it clear that we're not adding that c to itself infinitely many times. You're taking the antiderivative of each term, each piece, and then you put a plus c at the end, just like you did before when you were taking antiderivatives back in Calculus 1 and at the beginning of this course. Okay, so those are our rules for antidifferentiation and differentiation. It looks hard, it looks much worse than it is. That we should also talk about convergence. It turns out if f converges on the interval negative c plus r, or excuse me, c minus r to c plus r, then f prime converges on that interval as well, and the antiderivative of f converges on that interval as well. So f prime, and its antiderivative all have the same open interval of convergence. And what I mean when I say open interval of convergence is that if this one converges on negative 2 to 2, this one converges on negative 2 to 2, and this one converges on negative 2 to 2. The only place where they might differ is at the endpoints. So I'm going to write, they may differ in their convergence at x equals c plus or minus r, so at the endpoints of the interval. So this is nice. If you already know where a power series converges, you can take its derivative, and you know almost all of where the derivative converges. You also can take its antiderivative, and you know almost all of where that antiderivative converges. The only thing that you might have to check is the endpoints, if you need the interval of convergence for the new series. Okay, so let's do one more example. Let's say I have the sum as n goes from 0 to infinity of 3 to the n times x to the n over n factorial. That's my f of x. And we're asked to find the antiderivative of f of x as an infinite series. The antiderivative of f is the antiderivative of this now again, I am just focusing on the x to the n. All the rest of that is constant. And so I get the sum as n goes from 0 to infinity. I bring out my constants, the 3 to the n and the n factorial, and I anti-differentiate x to the n with respect to x. So I'm really just focused right here. And I get this, 3 to the n over n factorial. That's n times x to the n minus 1, and then we have a plus c over here. And that n and n factorial, that will reduce. So n over n factorial is n over n times n minus 1 factorial. The n's reduce, and we just get a 1 over n minus 1 factorial. So I'll simplify that this way. Now, if you're not sure about this yet, if you're like, I feel like I can follow your rules, but I don't really get it. One thing that helps students to get it is to expand this and then show themselves that when I expand this and I take the antiderivative, I get the same thing that I got right here. Let me show you. I just took the derivative, not the antiderivative, didn't I? I'm so sorry. Just kidding, don't do that. Add 1 to the exponent, divide by the new exponent. There we go. Add 1, and n plus 1 times n factorial is n plus 1 factorial. Wow, that's a big old mistake. That's okay. We all make mistakes, right? It's okay to make mistakes every once in a while. You just have the humility to correct them. No big deal. You learn from your mistakes and you move on. Okay, so I got this as my antiderivative. Now, just to confirm, just to make sure I understand the concept, make sure you understand the concept, let's expand this, take the antiderivative term by term, and see that we get exactly the same thing as this. So I'm looking at this series now, and I want its antiderivative. And I'm writing this out explicitly again so that I can remind myself exactly what it is we're doing when we do this. When n equals 0, this is 3 to the 0 times x to the 0 over 0 factorial. 3 to the 0 is 1, x to the 0 is 1 provided x is not 0, and then 0 factorial is defined to be 1, so we just get a 1. When n is 1, we get 3 to the first times x to the first, so that's 3x over 1 factorial, so we just get a 3x. When n equals 2, you get a 3 squared, that's 9, times x squared, all over 2 factorial. When n equals 3, you have 3 cubed, so 27, times x cubed over 3 factorial, so 3 times 2, and 3 goes into 27 9 times. Okay, now when I take the antiderivative of this term by term, the antiderivative of 1 is x. Then here I bring my 3 down, just like we did over here. We brought our constants out, and I take the derivative of x to the first, antiderivative of x to the first. So I add 1 to the exponent, and I divide by the new exponent. The 9 over 2, I bring that down. Then I add 1 to the exponent and divide by the new exponent. Then over here I've got another 9 over 2. Then I add 1 to the exponent and divide by the new exponent. And then when we simplify, we get this. 3 goes into 9 3 times. Oops, it's off the screen, sorry. Now I claim that this is the same as that right there. Let's check it out and make sure it's actually the same. So let's expand that series and show that we get the same thing. So I've got the sum as n goes from 0 to infinity, and actually I would get all of this plus c. Let's make sure to say that, plus c. Of c plus 3 to the n times x to the n plus 1 over n plus 1 factorial. So I have c plus, when n equals 0, we get 3 to the 0 times x to the 0 plus 1, so that's x over 1 factorial, so we just get x. When n equals 1, I get 3 to the first times x to the second over 2 factorial. When n equals 2, 3 squared is 9 times x to the 2 plus 1, so that's x cubed, over 2 plus 1 factorial, so that's 3 factorial. N equals 3. 3 cubed is 27. 3x to the 3 plus 1 is 4. Hey, isn't that what I did right there? I added 1 to the exponent, and then I divide by 4 factorial. And then keep going. Now, if you're saying to yourself, Ms. Townsend, that does not look exactly like that, you're right, it doesn't. But if we expand those factorials and simplify, I think we'll see that this is the same as that. Let's go just a little bit further. I have c plus x plus 2 factorial is just 2. So that matches with that. That's good. And over here, 9 is 3 times 3. 3 factorial is 3 times 2. And the 3's reduce. So we're good there. Over here with the 27, that's 3 times 3 times 3. 4 factorial is 3 times 2, or 4 times 3 times 2 times 1 times x to the 4th. The 3's reduce, and we get 9 over 8. Question is this the same as this? X, somehow I wrote 2 over 3 when I meant 3 over 2. X, 3 over 2 times x squared, we're good. 3 over 2 times x cubed, we're good. 9 over 8 times x to the 4th, we're good. Yes, so these are the same, which means we don't have to do all that. Doing that is the same thing as doing this. You focus on this guy, you take the antiderivative of that, x to the n plus 1 over n plus 1, and do a little algebra to simplify. And that will give you the antiderivative of the function. Okay. Now we did not talk about convergence in this one, but we'll talk about convergence in the next video.